Welcome to The Explainer. Today, we're diving into a massive, and I mean massive, breakthrough in how large language models solve complex problems. You know how frustrating it is to watch an AI slowly type out this incredibly long, tedious explanation just to give you the answer to a relatively simple math question? Well, if that's ever bugged you, you're going to find today's topic absolutely fascinating. We're unpacking a new research paper called Latent Thought Flow, Efficient Latent Reasoning in Large Language Models. And honestly, this proposes a fundamental shift in how artificial intelligence actually thinks. But to really appreciate the solution here, we've got to understand the problem. Why do these models waste so much time thinking out loud in the first place? Right now, to tackle a difficult task, AI is pretty much forced to spit out its intermediate thoughts word by word. We call this chain of thought. And sure, it totally helps the AI get to the correct answer, but it's computationally expensive and just incredibly slow. The model is literally bottlenecked because it has to generate human-readable text for every single tiny step of its internal logic. So here's our roadmap for today. We are covering 1. The AI language bottleneck. 2. The shift to latent reasoning. 3. Enter latent thought flow. 4. Balancing accuracy and efficiency. And we'll wrap up with 5. The future of AI thinking. All right, section 1, the AI language bottleneck. Let's look at exactly how current models handle logical problem solving and why it's dragging them down. Think of explicit chain of thought like a person who is physically forced to speak every single fleeting thought out loud just to solve a tricky math equation. I mean, it works, but it's exhausting, right? It creates this massive linguistic space bottleneck because token-by-token decoding carries a huge inference overhead. Now, the proposed fix for this is latent reasoning. This approach relies on continuous vectors and hidden computation. It's incredibly fast because the AI doesn't have to bother translating its complex math into English until the very, very end. Moving right along to section 2, the shift to latent reasoning. To fix all this slowness, researchers started exploring how AI might actually internalize its logic. The formal definition here is performing multi-step computation directly within an AI model's continuous hidden state space rather than decoding it into discrete text tokens. Basically, latent reasoning is like silent contemplation for AI. It lets the model internalize its work. It completely bypasses that tedious translation into human language while it's in the thick of solving the problem, and instead it just manipulates these dense mathematical vectors internally. But as you might guess, early attempts at this kind of fell short. They had these fixed reasoning budgets. What that means is the AI would take the exact same amount of hidden steps to solve 1 plus 1 as it would to solve advanced calculus. Doesn't make sense, right? They were also highly deterministic, which meant they were basically guessing blindly or locking onto a single path. The really crucial flaw was that these early models completely ignored whether a shorter, cheaper path could also get the right answer. They just didn't know how to balance being correct with computational cost. Which brings us to section 3, enter latent thought flow. This is the core of today's explainer, a highly efficient reward proportional framework known as LTF. This perfectly illustrates how the LTF system actually operates. Notice how it doesn't model reasoning as just one rigid, straight line. Instead, it's a continuous flow of variable length trajectories. Think of it like a branching river. The model naturally navigates this continuous space, deciding step by step whether it needs to keep thinking or if it's ready to terminate the process and deliver your answer. To navigate that river, LTF uses something called a continuous generative flow network, or GFlowNet. It learns a stochastic generative policy to match a reward-induced posterior. Okay, I know that sounds like a lot of jargon, but in plain English, just imagine a really smart GPS. Instead of giving you one single route that might run you straight into a traffic jam, it dynamically directs the flow of probability to multiple paths that are both highly accurate and computationally cheap. It preserves diverse, high-utility solutions. So how does it learn to do this? It's literally a 3-step dance, and the mechanics are just incredibly elegant. Step 1, the model samples a hidden path of continuous thoughts. Step 2, it judges the final answer. Was it correct? And, importantly, how much compute did it burn to get there? Step 3, it adjusts its internal probabilities. So if a path was correct but way too long, it gets less probability mass. But if it was concise and correct, boom, it gets more. It actively learns to favor concise efficiency. Okay, on to section 4, balancing accuracy and efficiency. The big question here is, how in the world do we actually guide an AI that's exploring this massive, completely unconstrained hidden void during training? To make this work, the researchers had to solve 3 pretty massive mathematical hurdles. First, Because thoughts are continuous vectors, they invented something called continuous subtrajectory balance to track the flow of logic. Second, since you only know if the math is actually right at the very end, they brought in entropy-weighted subtrajectory balance. Actually, think of that like focusing the AI's training on the most complex crossroads of its thought process. And finally, to stop the AI from drifting off into meaningless mathematical noise, they used a reference prior regularizer. These are basically semantic anchors that give the AI a starting point based on actual human reasoning before letting it optimize for speed. Let's talk numbers, because the data here is just awesome. What is the result of all that advanced math? Well, LTF improves accuracy by 9.5 to 12.9% across various tasks. And that is when compared to already strong latent reasoning baselines like Colar and Regular. But wait, it's not just more accurate. Take a look at this staggering number, 34.5%. That represents the average reduction in reasoning length on fine-tuning tasks compared to those exact same strong baseline models. Let that sink in. The AI is getting noticeably smarter, and it's doing it in a third less time. When you test it on the GSM 8K AugMath benchmark using a 1 billion parameter llama model, LTF's dominance is just super obvious. Standard explicit chain of thought takes over 120 computational steps to solve the problems. Regular is way better, bringing that down to 3.69. But LTF pushes the boundary even further down to 3.34 steps. It's reaching the correct answer with an absolute fraction of the steps used by standard models. Now you might be thinking, did it just memorize the test? Nope. Look at these transfer learning settings. The AI was tested on out-of-domain math datasets it wasn't explicitly trained on. Across GSM Hard, SVAMP, and multi-arith, LTF consistently beats the regular baseline. On SVAMP, for instance, it jumps from about 48% up to 52%. This proves for sure that LTF perfectly balances generalized, adaptable intelligence with serious speed. Which naturally leads us to our final section, Section 5, the future of AI thinking. What does this huge shift from loud, token-by-token generation to silent, continuous flow actually mean for the future of AI? The LTF advantage is a total game changer. It automatically adapts its latent budget to the problem difficulty, taking quick paths for easy problems and longer, more deliberate paths for the hard ones. It shows excellent performance even under extreme compression, holding on to its accuracy even when forced to use very few steps. And incredibly, it supports test time scaling. That means if you give the AI just a little more time to compute during inference, it can sample multiple compact reasoning trajectories to guarantee a highly accurate result, without generating endless walls of text. LTF proves we can break the linguistic bottleneck once and for all. Which leaves us with a fascinating final thought for you to chew on. For years, we've heavily relied on chain-of-thought prompting to peek inside the AI's mind, right? To see exactly how it got its answer. But if this new technology becomes the standard, if an AI's most brilliant, lightning-fast problem-solving happens entirely in a silent, mathematically optimal void, how will we ever be able to interpret the hidden depths of its mind? It's a massive leap forward for efficiency, no doubt, but a really profound new challenge for AI interpretability. Thank you so much for joining me for this explainer, and keep exploring.